All right, team, so this is the video for the registration theory homework. So this is after the registration theory class where we learn how to conduct a registration, how to determine total corrections to get a GFT setting, and then how to conduct a concurrent MET to isolate pause and then transfer pause, right? So we're just gonna jump right into it. Situation, so we're the FDO for Bravo Battery 3321, which is 6 Paladins. Right, our battalion is conducting live fire operations in local training area. Your FDC is processing live fire missions manually in an autonomous mode. Your battalion commander observed your accurate fires during the last field exercise and wants to see if your FDC again is capable of achieving first round fire for effects utilizing manual mech techniques. Okay, so basically we're going to answer some general knowledge questions first, and then we're going to get into a concurrent mech technique. So first things first, what do all registrations yield? Where I can find this is inside of my TC. Right, so the chapter on registrations is chapter 10. So let's go ahead and flip to chapter 10. So if you like this high-speed, smaller TC3-09.81, this is actually available on a website, myarmypublications.com. It's pretty good. It costs about, I don't know, $1520, something like that, but it's a good size I can keep in my pocket. So what do all registrations yield? So here in paragraph 10-3, we see that all registrations yield total corrections. All right, so we're just going to record total corrections. So what that means is a registration yields a GFT setting, and a GFT setting encompasses all of my big blue MET, all of my little blue MET, all of my pause, right? It has all of my MVV data, propellant efficiencies. It has all of my meteorological data. That's all encompassed in that, right? So number 2, how are total corrections determined in the third step to improving firing data? So how do we determine total corrections, right? Basically, after we shoot a registration, what do I do with my did hit data? So that's going to be in MET techniques. So that's going to be chapter 1.1. So let's refer to chapter 1.1. All right, chapter 1.1 is meteorological techniques. Right, and that should be here on page, yep. So our 4 steps to improving firing data are here on page 11-2. And I can see here in step 3, right, because it's asking about third step, I even have highlighted, we determine total corrections by subtracting should hit data from did hit data. So I'm just gonna record total corrections equals did hit data, meaning this is the deflection quadrant infused time that I shot in order to achieve the registration, in order to achieve the impacts on the registration point, minus the should hit data, meaning that's my basic like chart data, right? My first set of fire commands that I got that should have given me the achieved accuracy that I wanted, but I didn't necessarily get, okay? But again, that's the total corrections is equal to did hit data minus should hit data. So number 3, what is the observer's objective in the impact phase of a precision registration? Right, so remember impact phase, you know, if I'm aiming at a target here, the impact phase is whenever I'm shooting rounds, you know, and the observer is giving me corrections to get the rounds around the target, right? But how many rounds is he supposed to get in what particular, you know, in relation to the target there, right? So that's going to be back in chapter 1.0, right? Because chapter 1.0 is where we're going to discover stuff for registrations, right? Because this is registrations. So what is his objective, right? So let's look on page 10-5. Yep. So it even says right there, the objective. The observer's objective in the impact phase of registration is to obtain spottings of 2 rounds over and 2 rounds short along the OT line. So if this is my target, right? My gun's down here. This is my gun target line. The objective is to obtain spottings of 2 rounds over, so right over the target, and 2 rounds under, right under the target, right? Fired with the same data or from rounds fired within 2 5 meters apart, right? Meaning that all of this should be 2 5 meters. Okay, so that is the objective of the impact phase of a precision registration. So I'm just going to call that 2 over, 2 short, within 2 5 meters. Okay, So number 4, what will the observer report to the FTC when he or she is ready to conduct the registration? All right, that's probably still here in the same chapter. I could probably just turn the page, and I have it highlighted right here. So the observer's response. The observer doesn't know anything about the registration, right? We're going to tell the observer that we want to shoot a registration. So the way that the observer communicates to us that he is ready to observe is he's going to report his direction, right? So direction. That's the observer direction, right? The OT line. Okay, next is define the mean deflection line. So deflection line and probable error, both of these, we got to reach all the way back into chapter 3. So we'll reach all the way back into chapter 3 here, right? Because chapter 3 is ballistics. So this is the ballistic theory, and both of these are theory questions. So let's see here. I bet you both of these are on the same page. Yep, so I'm here on page 3-16. And on 3-16, it gives me a couple of different definitions. I'm actually going to do probable error first, right? So it says probable error is nothing more than an error that is exceeded as often as it is not exceeded. So 50%, right? An error that is exceeded as often as it is not exceeded. It's literally just, it just means 50%. Okay? All right. So probable error, done, too easy, right? We discussed this in class. If you need to see a more in-depth definition of this or a graphical definition of this, you can keep reading this paragraph or you can look at the slides in class. Okay, next one is define the mean deflection line. So mean deflection line up here. It says half the rounds will be to the right of, let me back up. A second line can be drawn parallel to the line of fire, again dividing the sample into 2 equal groups. Half of the rounds will be to the right of this line and half will be to the left. This line represents the mean deflection of the sample and is called the mean deflection line. So the mean deflection line is literally just the parallel line where half of the rounds will land left and right. They're along the gun target line, along the line of fire, right? That's the mean deflection line right here. So what I'm just going to do is I'm just going to say, I could reference that on page 3-16, we say paragraph 3-68. I'm just going to say figure, I'm just going to say just look at the figure, right? Because it's a graphical representation, the mean deflection line is. Okay, but I'm going to tab that page. I'm going to keep all these definitions highlighted. So probable error and range, probable error, mean deflection line, and mean range line. I'm going to keep all those highlighted. Okay. All right, so let's turn to the next page of our homework and move on to requirement 2. So requirement 2, the battalion FDO wishes you to conduct a registration with a lot of Mike 232 Alpha 1, lot hotel, that all firing batteries in the battalion have on hand. Your battery has been selected to register the battalion. Okay, so basically if we don't have MET, right, if the battalion for some reason doesn't have MET, none of the batteries can get MET. I've got 3 batteries in the battalion. What the battalion can do is be like, hey, what battery did we say we were? Hey, Bravo battery, you're going to conduct a registration, and then you are going to transfer all those registration corrections to the adjacent batteries, right? But let's look at here this first question. What will we transmit to the battalion FDO following the registration and our concurrent MET technique? Okay, so what specifically are we going to transmit to them? So let's look in chapter 1.1, which is where we have all of our MET corrections, right? Chapter 1.1, specifically, I think that's page 11-3. Yeah, here we go. Page 11-3. So here in table 11-1, it has our 5 steps to improving firing data, right? We've got steps 1, 2, 3, 4 over here, and then we have all these steps for expanded right here. I'm sorry, it's 5 steps to improving firing data. I don't know why I said 4. It says, what will we transmit to the battalion FDO? So basically, what do we transfer between units? It says right here, by quantifying all MET corrections, which is basically what we do for a concurrent MET technique and a registration, the position constants are isolated. Once this is completed, a unit can maintain first on fire for effect over time without adjusting. Also, these position constants are used to improve the firing data of other units. So I can transfer these pause constants. So what I'm going to transmit to the battalion FDO are my pause constants. Right, so remember that pause constants is part of our total corrections, right? MET, we've got big blue MET and little blue MET, which encompasses meteorological data. It encompasses our MVVs. you know, our propellant temperature, like all that stuff is included in the MET data, the big blue MET, right? And then over here in our position constants, these are things that are affecting our firing data somehow, but we can't necessarily identify, right? We can't identify them, but we can isolate them by, you know, defining and isolating all the big blue MET. I can then isolate and quantify my position constants or my pause. So then once I determine this, I can transfer that over to different firing units. So I'm going to transmit my pause constants after I shoot my registration and then conduct my concurrent mech technique to isolate pause. Okay. All right, so let's go on to the section. What two requirements must be fulfilled before you transfer that data to the battalion FTC or any other firing unit? So in here, if it's not already marked, go ahead and mark. There are two requirements we have to follow two requirements we have to have in order to transfer pause. The first is that common survey is established between transferring units. Common survey can be defined as orienting all concerned fire support assets in the same fashion with respect to direction and location. So basically what this means, our primary source of common survey for all weapon systems in the US military is GPS, right? So if they're all talking on GPS, we've already met requirement number one. If we're not talking on GPS, we have to establish common survey, which is the job of DIVARTY, right? With our aiming circles and all of our iPads and survey and things like that, right? So that has to be our first requirement. So number one, common survey. Okay. Then number two, the registering FDC must account for all measurable non-standard conditions in effect during the registration that affected the howitzer and the projectile. Okay, makes sense, right? We have to account for all measurable non-standard conditions, which is our MET. We have to be able to account for our MET. So I'll just say reg FDC must account for all measurable non-standard conditions, which makes sense, right? Because if I'm trying to transfer my pause, I have to know what all of my non-standard conditions are, all my measurable non-standard conditions. I got to know my meteorological information. I got to know my propellant efficiency. I got to know my shooting strength. I got to know my propellant temperature, my projectile square weight. I got to know all that stuff, right? I have to be able to account for all of those measurable non-standard conditions. That way I can isolate my pause based off my total corrections, okay? All right. So those are our general knowledge questions. Let's move on to concurrent MET. All right, so let's go ahead and execute the requirement 2 concurrent MET technique. So complete a concurrent MET technique given the GFT setting from a registration and following information in DA form 4200. So real quick, I'm just going to highlight so we can make sure that we're taking notice. All right, so this is a concurrent MET technique, okay, given the GFT setting from registration. So basically, we shot a registration. We determined our should hit and did hit data, right? This is just an example ROF. We don't have a ROF here in the homework, but just to remind you what we learned in class, right? We identified our should hit data, which is the information that I shot that should have achieved first round fire for effects, but didn't. Then I had to adjust my rounds on the target to eventually get my did hit data, right? Where we got 2 rounds over, 2 rounds short. And then using my did hit and should hit data, I determined a GFT setting using my UCarrot format, as well as my total deflection correction and my GFT deflection correction, okay? So we conducted this, and then we got this GFT setting right here, right? So I've got GFT Bravo, which means Bravo battery. We shot this with charge 3 hotel, Mike 222 Alpha 1. Lot Alpha hotel, so lot Alpha refers to the projectile, right? Lot hotel refers to the lot of propellant. So my should hit range was 8170, right? My did hit elevation was 220, and my did hit time was 20.9. So based off of that, I found my range at adjusted elevation, which was 8320. Range at adjusted elevation literally means that I went to my GFT or my TFT, set it off on elevation 220 and saw what the did hit range was. And then I found my range correction, my total range correction here, right? Total data is, remember we said that total data was my did hit data minus my should hit data, right? And then down here, this is my fuse setting at adjusted elevation. So if I went into the GFT or TFT and set off elevation 220, I would have extracted a time fuse setting of 21.1, right? And then this is my did hit time fuse setting. and I got a total fuse correction of negative 0.2, which again is my did hit minus my should hit data. So I got a total fuse correction of negative 0.2. And the other tricky thing about the GFT settings is not just this right here. I also have this, right? I got my total deflection correction, which was left 9. And then I had to find my drift at adjusted elevation, which we would have set off our GFT on elevation 220, read up on the manufacturer hairline, and extracted drift, and then subtracted that to get our GFT deflection correction, which is left 3, okay? All that has already been done for us, right? We've already been given the GFT setting. All we have to do is take this and then perform a concurrent met, right? So we're given the GFT setting, we're given some firing data that would have come from our ROF, and then we're giving a MET message that we had in effect when we shot the registration, okay? So a couple things that I'm gonna want, a couple materials I'm gonna need for my concurrent MET technique, right? I'm gonna need a fresh blank DA form 4200. So I'm gonna have that in front of me right here. I'm gonna have my TC that I'm gonna have here, right? I'm gonna refer to chapter 1.1, which is, let's see here, meteorological techniques. I'm gonna turn through here until I find my concurrent MET technique step action drill, right? So this is page 11-16. Is going to be our concurrent MET technique step action drill. We're going to go step by step together with this right here. We did this in class already, but we're going to use this right here, right? A DA form 4200 is very daunting, but I mean, honestly, as long as you go through the step action drill, you're going to be just fine. Once you do this 2 or 3 times, you'll be able to do this without the step action drill because it's a self-policing form. All of my known data, I just take all this, figure out where to plug it in, and then solve for the rest, right? So I'm going to have that with me. Also for my reference, I'm gonna have this in front of me. You may not see it on screen, but I'll have this next to me, which is my Christmas tree. Mine's a lot smaller than yours. But this is gonna tell me where all of this information came from and where it goes, right? So I can see what all tables I need to extract data from and everything like that. So I'm gonna have this in front of me off to the side so I can reference this in case I need it. But the step action drill should be pretty solid, okay? Make sure that we have our calculator, a 4-function calculator. We need that for everything, right? And then if you have it, you can print out the slides from the class, or you can just go ahead and take a screenshot of this and make your own notes. But I have my MET message, right? MET message validation, and then I have my temperature and density conversion equations, right? Because I guarantee you, let's look at it right here. Yep, we got a computer MET message, which is the primary, well, really it's the only way that we can actually calculate and transmit MET these days. We can no longer do ballistic MET messages, right? So we're gonna have to convert this computer MET message into a ballistic MET message eventually, right? Because the TFT is based off of ballistic MET data, not computer MET data, right? And so we just need to make sure that we also have our TFT. We're gonna be using the Alpha Romeo 2 for this today because we're shooting Mach 7, 9, or 5. All right, so let's just get right into it. So, solution of concurrent MET technique, right? It says right here, record the known data from the registration on a DA form 4200. Use the ROF shown in a figure. So we could refer to a different figure on a different page, but we're just gonna go ahead and record all of our known data from our registration, right? Which we can start up here. So charge is gonna be 3 hotel. All right, let's see, do we have an adjusted quadrant elevation? Yes, we do, it's 210. Okay, we have a chart deflection, so I'm just gonna go ahead, well, we'll use that here in a bit. I got my adjusted deflection, here we go, azimuth of Valet, use that here in a bit. I've got the Bravo battery altitude, gonna use it here in a bit, latitude, projectile square rate, prop temp, yep, okay. So the other thing that I get for my registration is my safety T, right? So, or not my safety T, my lazy Z. So I'm just gonna go ahead and record the appropriate data down here. So I'm gonna basically just take this half of the lazy Z and record it right here. So range 8170, total range correction of 150, to give me my did hit range of 8320. Did hit elevation was 220. Time fuse setting at adjusted elevation is 21.1. Total fuse correction is negative 0.2. And did hit time fuse was 20.9. So I'm just gonna go ahead and record that down there, right? Looking at our Christmas tree, there's some other other shells that we can go ahead and fill out now, so we don't have to fill out later, right? So one of them I'm going to need up here is my total deflection correction and my met deflection correction. I can just go ahead and set up that equation right now, right? Or at least the shell of the equation. So I don't have to come back and try to find it later. So total deflection correction minus met deflection correction. Okay, that's going to yield my pause deflection correction. Okay, so I'm just recorded that right there. Okay, I know up here I'm going to have to do this stuff eventually, so let's go and record it. So I have my common deflection minus my chart deflection, and that's going to give me my delta df, or my delta deflection, or yep, delta df. Okay, then I'm going to eventually get my azimuth of lay. I'm going to add my delta deflection to give me my overall direction of fire. Okay, and eventually I'm going to need to use that to determine my chart direction of wind, which we'll get to here in a bit. Let's see what else, what other shells I can fill out here. Because you got this one down here, right? I've got this down here for my met range correction. I've got VE. And the reason I'm recording these right now is because, like, I'm going to have to record these for every single DA Form 4200 I do. So I might as well just go ahead and fill them in now, right? So velocity error minus MVV. This is technically incorrect. It should say minus delta MV, right? In this particular case, we don't have a delta MV because we're shooting paladins, right? If we were shooting a 777, we would definitely have a delta MV weapon, but we're shooting a paladin, so we don't need it. And all that's going to be my pause VE, or my pause velocity error, okay? All right, let's see, what else can I fill out? Yeah, so we're going to fill that out here in a bit. Fill this out here in a bit, okay. All right, so we have pretty much all of our known data, and let's just start following the step action drill, okay? So, starting, we started step 1, so record the charge, record a line through the adjusted quadrant elevation block. A line through the adjusted quadrant elevation block. Well, we don't need that because we're going to be using our adjusted quadrant elevation to find our met line number, so we're going to go ahead and do that. Record the chart range in both blocks. Okay, so chart range. Where's our chart range? Oh, there it is right there. Chart range is our should hit range, which is 8170. Okay. We got our chart range in both blocks, okay? 8170. The second block is down here. Chart range 8170. Chart range and should hit range on the lazy Z are the same thing, right? So range 8170 is both my should hit range. This is my should hit range and my chart range, okay? So next we record the latitude to the nearest 10 degrees. Okay, so what latitude are we in? Let's see here. Latitude, right here we are 20 degrees north. Okay, so we're going to record latitude 20 degrees north. Try to set this up so we can see it on the camera and follow along here on the steps. Okay, we'll do it just like that. All right, next I record the battery altitude to the nearest 1 meter in parentheses and to the nearest 10 meters in the block. That's going to be right here, the battery altitude, right? We said the battery altitude here was 411. In 411, we express this to the nearest 10, so we're going to record 410 right there. Okay, done. Next, record target altitude and altitude of burst to the nearest meter. Okay, so the altitude of the target. So the altitude of the target in this particular case, because we're shooting a known point, is the altitude of the known point. So the altitude of the known point was 330. So we're going to record that right there, 330. And that's the altitude of the known point and the altitude of the burst are the same thing, 330. My printer did not print this line for some reason. Okay, so 330. Okay, done. Next, we record the direction of fire to the nearest mill in parentheses and to the nearest 100 mils in the block. Use the following diagram to show how to determine the direction of fire. So our direction of fire is this equation that we set up over here, right? And that's going to be our common deflection minus chart deflection. Then we're going to take that and then add that to the azimuth of fire. Okay, so what did we say that our common deflection was? Common deflection for all U.S. howitzers is always 3,200. All right, minus our chart deflection. What was our chart deflection here in our known data? It was 3266. I would have gotten that from my ROF. Okay, so let's pop that into our calculator. 3200 minus 3266 should give me negative 66. So delta DF is negative 66. Okay, so now I take my azimuth of layer, my azimuth of fire, which was 1500. And then I add my delta DF that I just calculated, which is negative 66. 1500 minus 66 gives me a direction of fire of 1434. Okay, so now I got that. Let's go back to the step action. It says, record the direction of fire. Okay, so I record that down here, right? So 1434 in parentheses, and then to the nearest 100 mils and the block to the right, which is 1400. Okay, too easy, done. Record the total deflection correction in the wind components and deflection computational space. So we need to get our total deflection correction, right? What was our total deflection correction? We said here it was left 9, right? Sorry, let me get back here. Computation space, right? So total deflection correction minus met deflection correction equals pause deflection correction, which is over here. So we said our total deflection correction was left 9, right? Okay, so we've got that. Next, we record in the met range correction section the square weight of the projectile fired during the registration. Also record the standard projectile weight, which can be determined in the introduction of the appropriate TFT, okay? So what square weight did we shoot here? We shot 4 square for this registration. So there's gonna be references inside of the step action. It says like 3 square, right? It's just referring to like a scenario that the TC is giving you. But we shot 4 square. Right? It says also record the standard value, which is also 4 square. Okay. Next, we record the MVV of the howitzer that fired the registration. Okay, use the equation, and we squared in VE minus delta MV weapon minus MVV gives us our pause VE, which is what we recorded here, right? We said that our base piece MVV was negative 7.1 from our known data. Okay. So we recorded that. Record the MVV. Done. Let's turn the page. All right, next we're on step 1 kilo. Record the propellant temperature at the time of registration. So our prop temp down here is positive 72 degrees. So we're going to record that right there. Okay. Done. Next, 1 Lima. Divide the MV unit correction block in half with the diagonal line. My DA form 4200 already has it. If yours does not, go ahead and draw that line right there, okay? Next, record the lazy Z in the bottom of the computational block. We've already done that. That's one of the first things that I like to do. I like to get my lazy Z out of the way first. So I went ahead and recorded that, okay? Next is 1 November. Record the total range correction in the top block and line out the bottom block. Okay, so our total range correction, it goes up here for the total range correction block, which we said right here was positive 150. And then we line out the bottom block, which is done, okay? Here, 1 Oscar, record the total fuse correction in the top block and the line out of the bottom block. So total fuse correction is gonna be right here, which for us is negative 0.2. Okay, and my bottom block is already lined out because this is a DA form 400 set up for concurrent met, okay? Next is 1 Papa. Record the fuse setting corresponding to the adjusted elevation to the nearest 10th, and then express it to the nearest whole fuse setting increment. Record it in the space to the left of the words met fuse correction as follows. Fuse setting should have a square here. Fuse setting at adjusted elevation, right? So fuse setting at adjusted elevation for us, that's our fuse setting at adjusted elevation right here, which is 21.1. which we then express to 2.1. The reason why we express this right here is just because we're gonna need this to go into our TFT. We need fuse setting at adjusted elevation to the nearest whole second because I don't wanna have to interpolate, right? Which we'll discuss here in a bit. Next step is 1 Quebec, record the known point number. So I'm gonna record the known point number down here in target number, and we said that we were at known point 3. Okay, that was on our known data over here. Next is record the unit designation. We said we were Bravo battery. Too easy. Next, 1 Sierra, record it says 1/3 April 2016 time group. It means date time group, right? So we're gonna go ahead and record the date time group right here. So date time group, so at least for me right now, the date is 08. Remember, we always record time in Zulu if we can. My Zulu time right now is 46 Zulu. And this is April 2-3. So this is how we do date time groups. Okay, so I got date time group. Where are we? So we recorded the date time group. Next, determine the MET line number of the MET message from table alpha. We should square in table alpha for concurrent MET technique. We're going to use table alpha and the height of target above gun. We don't need the height of target above gun because table alpha just uses the adjusted quadrant elevation, right? So we're going to refer to our TFT. So TFT, make sure I'm charge 3 hotel, Mike 232 alpha 1. And what did we say that our adjusted quadrant elevation was? It was 210. So adjusted quadrant elevation 210 falls between 168.2 and 259.1, and that gives me MET line number. It says 2, but if we haven't already done so, we need to go ahead and square in zeros in front of all these numbers because MET line numbers are always 2 digits. Okay, and I'm on page 339 of my Alfa Romeo 2. Okay, so MET line number 2. What do we do with that again? It says determine the MET line number. Okay, so we determined it. Next, we need to record the MET message data. Okay, so I'm gonna look down here in my MET message that I got that was active during my registration. What I'm gonna do is I'm gonna highlight line number 2. Line number 02, okay? So I've got my admin data up here at the top. I've got my MET data, and then I'm looking at line number 2. I'm not looking at any other line numbers. That means that based off of the adjusted quadrant elevation, which is how high the tube is pointing, right? That means that the projectile will travel through line 0, line 1, and line 2 of MET. So because line 2 is the one that it's gonna peak at, that's the line that I wanna calculate all of my MET data for, all right? So next, we're going to start recording the MET message data on the DA form 4200. The computer MET message is shown in figure 11-13 on page 11-28. So the one that's used in the example in the TC, but we're using the one that's down here in our homework, okay? First, 3 alpha, determine the corresponding computer MET message line number. For line number, determine step 2, which we already did. For us, it is line number 2, 0, 2. Done. 3 bravo, determine the corresponding weathered standards for air temperature and density. Right, at the determined line number. So air temp and air density. For us, our air temperature is measured in Kelvin, right? So this is 2279, and this is 227.9 Kelvin is what that is, okay? And then our barometric pressure is 927 millibars, right? So we're right here, yep, at our determined line number. Next, we need to extract the computer MET air temperature and air pressure. Yep, so that's what we did. We got the air temperature and air pressure, and then we got to convert the computer MET air temperature and pressure into simulated ballistic data with the following equation, okay? So I don't necessarily like how the equation is written in the TC. It doesn't really make a whole lot of sense to me. So what I do is I use this equation here. So if you want to take a second and pause to write this down or screenshot it, this is the equation that I'm going to be referencing whenever we are converting this data, okay? So we need to convert Kelvin and millibars into the air temperature and air density that that we need for our DA form 4200, right? So we're going to do that. We can do it here in this lower computational space where there's like room, but I always like to do it on the back because I don't ever have enough room. I don't write small enough. So I'm gonna flip this over and do this on the back. Okay, so what I'm going to do is on the back of my scratch paper here, I'm just going to record for MET line 2. For MET line number 2, let's see here. My temperature in Kelvin is equal to 227.9. 227.9 degrees Kelvin is what my temperature is in my MET message, right? And then my pressure and millibars is equal to 927, right? And I need to convert my temperature in Kelvin to Fahrenheit and my pressure in millibars to air density is what I need, right? And when we say Fahrenheit and like the density, it's a percentage of standard is what we need, right? So what we have in a computer MET message is not what I need. I need ballistic data. So I'm going to use this equation right here, all right? So let's see. So I'm going to do this first one to get my air temp percent of standard. So air temperature from computer MET message in degrees Kelvin, we said that was 227.9. divided by my standard air temperature from page 11-3, figure 11-8. Okay, so I need to refer to page 11-13 in my TC. Okay, so I need to find standard air temperature from page 11-13, figure 11-8. So 11-8 is stair condition. Okay, yep, line number 2. I see for my standard in degrees Kelvin, it is 285.9. Okay, so just got that. Next, I'm going to multiply those times 100, and then that's going to give me my air temperature percent of standard to use in the DA form 4200 expressed to the tenths. So let's do 227.9 divided by 285.9 multiplied times 100. Okay, so that gives me 79.71318, right? But it says here I need to express this to the tens, which would be 79.7. Okay, so that's what I'm going to use as my air temperature of standard in my DA form 4200. Okay, so now that I have that, let's go down here. So next I need to get to my air density percent of standard. So air pressure from computer met message in millibars. My pressure, we said, was 927, right? So 927. Okay, 927 multiplied times this wild number, 0.348366764, okay? And then we're going to divide that result by air temperature from computer met message in degrees Kelvin, which we saw down here or up here was 227.9 degrees Kelvin. Okay, then that's going to get us our air density in kilograms per meters cubed, which we're going to express to the thousandths. So 927 times, I don't think this is going to fit my calculator, 0.348366764. Yeah, it's not going to fit, but it's close enough. It's going to be that number divided by 227.9, which gives me 1.4170107. Okay, so I need that to the thousandth. So I need 1, 2, 3, 4. Okay, so I need 1, 2, 3, 4. So that will express to 1.4170. Okay, so now I'm going to take that and then plug that into this equation. So I'm going to take that value that I just calculated, 1.4170. Then I'm going to divide that by standard air density from page 11-13, figure 11-8, in kilograms per meters cubed, okay? So standard air density, so for line 2, it's 1.1844. Okay, then I'm going to take that, and then I'm going to multiply that times 100, and that's going to give me my air density percent of standard ratio. Okay, so let's do that. So 1.4170 divided by 1.1844 multiplied times 100 gives me 119.63. What do I need? I need it to the tens here. So 119.6. Okay. And now that I have that, I need to go ahead and take that value and then multiply that times the density weighting factor from page 11-3, figure 11-9. Okay, so density weighting factors right here for line 0 through 03 is 1. Sweet. So 1196 times 1.0000 gives me 119.6. So that is my density percent of standard. And this up here is my temp percent of standard. Okay. So now I'm going to use those values whenever I have to plug it back into my concurrent net technique. So let's go back to our step action drill. Okay, so let's see here. Extract, multiply. Yep, so record data from the identification. Or I'm sorry, let me back up here. Record the derivation. I don't know what that word is. Record the derivation computations in the met message section computational space. So basically what we just found, we need to record in our computational, we need to record a computational space, which is, back here, and we record these values up here. So we said our air temp percent of standard was 79.7. That's what we solved for, right? Our air density was 119.6. Okay, so now we have that. Record, so I'm here on 3 hotel. So record data from the identification line. So we need to record the, let's see here. So the type of message is METCM. That means a computer met message, right? The octant is 01. The area or the unit, and this is in lat long, is 201, latitude 201, longitude 984. Not too important for us. We don't really care about that right now. Okay. Next, I record the date. So the date is 1-2. The time is 1250 Zulu. This is always going to be in Zulu time. Okay. And then I have my altitude of the MDP. All right, so this is one that you got to make sure that you don't get confused on. So in the computer met message, this is going to be encoded. This is in tens of meters. Okay, this is in tens of meters. But here on the DA form 4200, I want this in ones of meters, right? So this is actually 470. Okay, so altitude of the MDP is 470. Okay. And then my pressure in millibars right here is 942. Okay, so now I have that. So down here I come to 3 India. Next, record the altitude of the MDP, the wind direction, wind speed, air temperature, and air density from the met message. Okay, so the altitude of the MDP we said right here was 470. So my altitude of the MDP is going to be 470. So I got that. Okay. Wind direction, so the wind direction right here, we said the wind direction, so this is in, this is also in tens, right? So 120 is actually 1/200, so wind direction is 1/200. All right, wind speed, this is in singles, this is 8 knots, okay, wind speed is 8. And then it said, what else do we need? Air temperature and air density, which we've already calculated and recorded there, so we've already got that, right? It says data from the note, and we highlighted the note. Data from the met message must be decoded before being recorded the DA form 4200, which is what we just did together, okay? Next, so I go on to step 4. Step 4, compute delta H and chart direction of wind. So my delta H, the way that I do that is I go to 4 alpha. Determine the difference in altitude between the battery and the MDP to correct the values for air temperature and density. Circle the word above or below as appropriate. And that equation is altitude of battery minus the altitude of the MDP. So for us, the altitude of the battery is 410 minus the altitude of the MDP, which is 470. So we'll take 410 minus 470 to give us -60 is my delta H, right? And is the battery above or below? Okay, so the way to think of this is that, is the battery number lower or higher? The battery number is lower, so battery is below the MDP. Okay, below the MDP. All right, so now that we have that, now we subtract the direction of fire from the direction of wind to determine the chart direction of wind. Add 6400 to the direction of wind if it is less than the direction of fire. Record the actual wind direction in parentheses and express to the nearest 100 mils in the block. Okay, so that's this step right here. So my direction of wind, we said, was 1/200, right? I got it up here, or I can refer to it down here. Direction of wind is 1/200. Okay, so is this less than the direction of fire? Yes, it is, so I need to add that 6400. So 6400 plus 1/200 gives me 7600. Okay, so now that I have that, I take 7600 minus 1400 to give me my chart direction of wind of 6200. Okay, so now that I've got that, next is for Charlie. Record the wind speed in the crosswind and the range wind box. So the crosswind and the range wind is right here. I need to record the wind speed, which we recorded was 8 knots. All right, so I've got that recorded. So now I'm done with 4. Next is I need 5, step 5, extract the complementary range from table Bravo. It even tells me what table to go to, look at that. Okay, so I'm gonna refer to my TFT, I'm gonna go to table Bravo. All right, my entry arguments for table Bravo are range, as well as my VI, right? So it says enter table Bravo with the chart range expressed to the nearest 100 meters. So what did we say that our chart range was? Our chart range was 8170, which expressed to the nearest 100 meters is probably gonna be 8200. So let's look for the appropriate page. Okay, so there's 8200. Yep, the other thing I need is my VI expressed to the nearest 100 meters. So what was my VI? Right, our VI is target minus battery, right, which is going to be the height of target above gun. So if you said that our altitude of the battery was 411, that's going to be 330 minus 411 is going to give us a VI of negative 81, which expresses to negative 100 for table Bravo. Okay. So 8200 and negative 100. So 8200 and negative 100. Let's see here. I come together and I see that my complementary range is going to be negative 6. And if I needed to get my met line number, I would drop the ball down the stairs and see that it'd be met line number 02. So comp range is negative 6. All right, so we extract the complementary range, record the value in the complementary range block in the met message section. Yep. And then apply it to the chart range. The result is the entry range to the nearest meter. Express the value to the nearest 100 meters and record it out to the side of the entry range block. Okay, so we're going to take chart range of 8170 minus our comp range of, well, we apply this to 8170, which gives us an entry range of 8164, which then expresses to 8200. Okay, and this is going to be my entry range. So if you need to like circle it, highlight it, star it, whatever you do, this is my entry range that I'm going to be using for my TFT. Okay. All right. So now that we have that, let's see what we got. Next we go to C, extract the wind components from table Charlie. So let's refer to our TFT to table Charlie. So the step action drill gives us all the answers. It tells us exactly what to do. So extract our wind components from table Charlie. Enter table Charlie with the chart direction of wind. Extract and record the crosswind components and the range wind components. So we solved for the chart direction of wind, which is 6200, right? So I enter with 6200, and I see that my crosswind component is going to be left 0.20. So I'm going to circle left 0.20. And my range wind right here is going to be a headwind of 0.98. Okay, so table Charlie data extracted. Multiply the wind components by the wind speed and then express the result to the nearest 1 knot. I'm on step 6 Bravo here at the bottom of page 11-19. Okay, so I can see right here my equation's already set up. So I multiply my wind speed times the value that I extracted, right? So 8 times 0.2 gives me 1.6, right? It's going to be left 1.6, which expresses to left 2, right? Because I express that to 2 because it says express the result to the nearest 1 knot. Okay, and then let's do the same thing down here. Make sure I'm doing this in the right order. Multiply the both wind components, yep. So 8 multiplied times 0.98 gives me 7.84, which still expresses to 8, and it stays headwind. A headwind of 8 knots. Okay, so now that I have that, I can move on to my next step, which is turn the page here to page 11-20. Step 6, Charlie. The range wind and crosswind are now known values. The range wind is recorded in the known values block under the met range correction section. Okay, so the met range correction section right here are now known values. So now we can go ahead and record these. So what did we say that my range wind was? We said our total range wind was a headwind of 8 knots. I'll just go ahead and put knots here. You don't have to put knots. I'm just going to put knots just so we know what it is. So range wind of head 8 knots. Let's see here, range wind and crosswind. So now I can go ahead and put my crosswind. Yep. Okay. So yep, that's already good to go. We got to do some stuff with the crosswind here in a bit. Let's see here. Yep. So next we're going to move on to step 7, determine the temperature and density corrections from table delta. So let's extract our TFT, go to table delta right here. All right, so in the TFT, I'm on page 355, table delta. It says enter table delta with the delta H. So basically we need to find our delta H corrections to apply to our air temp and our air density. Okay, so we say that our delta H was. Delta H we said was -60. So whenever we enter table delta, always assume that this is a 3-digit number. So that's 060, so 060, right? I come in and I see that I have 0.1 as my DT, and I have 0.6 as my DD. So I'm going to record 0.1 and 0.6, but I need a sign for those, right? So let's look at the notes. If delta H is battery height, yep, we're tracking that. So number 2, if above the MDP, use a sign before the number. If below the MDP, which we are, use a sign after the number. So the sign after the number for hours, where are we? Here we are, is positive. It's positive for both. So positive 0.1, positive 0.6. Okay, so we've got that. So we extracted them, apply them, and record the result in the corrected values block and in the known values column of the met range correction section, which is down here. So I take 79.7, then I add 0.1 to get 79.8, and then 119.6 plus 0.6 gives me 120.2. Okay, now very, very important. As soon as I immediately record these, take this value and put it down here. Don't use this one, take this one. It has to be the corrected value down here for air temp, which would be, like we said, 79.8. And then 120.2. Okay. So now that I'm done with that, next I move on to step 8. Determine the correction to muzzle velocity for prop temp from table echo. So 8 alpha, enter table echo with prop temp to the nearest degree Fahrenheit. So we had prop temp of 7.2. Let's go to table echo. Okay, so now we're going to need to interpolate as necessary. So what is our prop temp? 7.2. Is that a listed value? No, it's not. So we're going to have to interpolate. So we need prop temp at 7.2 degrees. So don't know what it is for 7.2. 7.2 is not a listed value, but it does fall between 7.0 on top and 8.0 on bottom. All right, trying to find the effective muzzle velocity there. If it's not already marked, we're just going to go ahead and just cross through Celsius. Make sure we don't accidentally try to pull data for Celsius because this is America. Yep, okay, so 7.0, so 0.0. And then 8.0 is going to be 1.7. Set up our brackets. Little bracket on the left is going to be 2. Big bracket is going to be 1.0. This one's going to be x. This one's going to be 1.7. So I have 2 over 1.0 equals x over 1.7. Okay, so let's cross multiply. So that's going to be 1.7 times 2 divided by 1.0. 1.7 times 2 divided by 1.0 gives me 0.34. Express the x to the value of the column on the right. So 1.34 expresses to 0.3. Okay, and then I'm going to apply that to 0 to make the value fall between these two values. So that would be 0.3. Does that fall between these two values? Yes, it does. So my effect on muzzle velocity due to my prop temp is positive 0.3 meters per second. Okay, so let's see here. So we got that. So we interpolated, we recorded the value. Next, we need to determine variations from standard. The known values for range wind, air temperature, air density, and projectile square weight have been recorded in the known values column under the met range correction section. Yep, which we have right there. Compare the known values to the standard value, which is our standard value here. Circle the I for an increase or the D for a decrease, and then record the difference in the variations from standard column. Transfer the values to the variation from standard column in the met fuse correction section. Okay, so we're going to find them here and then pop them down here. All right, so let's do this first one first. So we have a headwind of 8 knots with a standard value of 0, which means our variation from standard is a headwind of 8 knots. Right, so for this one, this value is always going to be the same one here. Okay, so you have headwind of 8. Okay, next, if we have an air temp of 79.8%, so I'm just going to put percent there so we know what that is. Standard is 100%. What is the difference? I have a decrease of 20.2. Decrease of 20.2. Okay, next, after that, let's find our air density. So if air density is 120.2% and my standard is 100%, I have a increase of 20.2. Trip me up for a second because the air temp and the air density values are the same, just one's decrease, one's increase. Okay, then for projectile square weight, I'm shooting standard projectile square weight, so I don't have any variation from standard, so I'm just going to call that 0. Okay? All right, so now we take those and we pop them right down here. Okay? So we said that our range wind was head of 8. Our air temp was a decrease of 20.2. Air density was an increase of 20.2. And projectile square weight was change of 0. All right. So now we have accomplished step 9. Next is step 1.0. Determine unit corrections for drift, crosswind, muzzle velocity, range wind, air density, air temp, and projectile weight from table Fox. Okay, so let's do 1.0 alpha first. Enter table Fox with the entry range. Entry range, remember, we marked up here, right? Okay, so let's go ahead and find that. So come up here to table Fox. We said our entry range was A200. So going to be here on page 361. Page 361. Okay. Okay, so we have entered the table box with the entry range. Next, 10, 10 Bravo. Extract the azimuth correction for drift from column 8. Okay, so column 8 at range 8200 it would be left 6.4. Okay, well, what do I do with that? Let's see here. Drift, yep. So record it for drift, right? So we're gonna record drift is gonna be, what we say? We said it was left 6.4. Okay, left 6.4. All right, next, 10, yep, we got that. 10 Charlie. Extract the crosswind unit correction from column 9. So entry range of 8200, column 9. All right, I'm seeing 0.41. Okay, so we extract that. And then, well, it doesn't say where we record it, but we're going to record it right here. 0.41. We get that from table Fox, column 9 right there, okay? Next is 10 Delta. Extract the range correction for muzzle velocity from columns 10 and 11. So we're going to extract both of them because it is unknown at this time if the muzzle velocity effect will be an increase or a decrease. So we're going to extract both of those and put those down here. So 1011 for range 8200. So that is in the decrease column, which we're going to say decrease. The decrease column is going to be positive 19.8. And the increase column, it's going to be a negative 19.4. Okay. All right, so done with that. Next, we extract the correction for range wind from column 1-2 for a headwind or column 1-3 for a tailwind. We have a headwind, so we need to go ahead and extract that. So headwind at 8200, I see right there is 6.0. So I'm going to take that. I'm going to put that down here in my unit corrections, making sure that I carry the sign, positive 6.0. Okay, and because that I know that I'm going to have a positive multiplied times a positive, and what you can do is, if this will help you, you can put like little multiplication signs here, right? Positive times a positive is going to give me a positive value, so I can just cross through that minus block because I know that's not going to be anything, okay? So what was that? That was range wind, yep. So next is 10 Fox. Extract the correction for air temperature from column 1-4 for a decrease or column 1-5 for an increase. So we have a decrease in air temperature. So column 1-4, decrease at 8200 is negative 2.9. I know that a positive multiplied times a negative is going to be a negative, so I can just cross through this plus box right here. After that is going to be 10 Golf. Extract the correction for air density from column 1-6 for a decrease or column 1-7 for an increase. So for density, I have an increase. So A200, air density increase, that's column 1-7. Whoop, and that looks to be positive 28.6. All right, and then I know that a positive and a positive is going to give me a positive result, so I can just cross through this minus box right there, okay? All right, so let's move on to the next page. So let's flip over to page 11-21. Okay, so we need to extract the correction for projectile square weight from column 1-8 for a decrease or column 1-9 for an increase. This correction will be recorded with a ending of 0.0. All right, for us, it's going to be 0, right? Because we don't have any change, so the unit correction is going to be 0 because we are shooting standard, right? So we're not going to have a plus or a minus, okay? Next to unit corrections column, there are two columns, plus and minus. If the unit is plus, cross with the minus. Okay, so we've been doing that as we went, okay? So 10 India, we've been doing it as we go. Next is 10 Juliet. Multiply the crosswind unit correction by crosswind value and record the result to the nearest 0.1 in the crosswind correction block, which is all the way up here, right? So we're going to take, so 2 times 0.41. It's going to give us 0.82 to the nearest tenth, which should be, keep the same sign, which is left 0.8. Okay. Let's see here. Where were we? Yep, so we just multiplied that. Next, we go to 10 Kilo. Multiply the variation from standard by the unit corrections and record the results to the nearest tenth in the boxes that are not crossed out. So Make sure that it, yep. So now we're just gonna go ahead and perform this math down here. So starting at the top, so 8 times 6.0 gives us 48.0. Put that in the plus column. Okay, next is 20.2 multiplied times negative 2.9, which is gonna give me, hold on here. That was not correct. 20.2 multiplied times negative 2.9, which is going to give me negative 58.58, which expresses to negative 58.6. We do all this to the tenths. All right, next is 20.2 multiplied times positive 28.6, which gives me 577.7. Okay, and then I have 0 times 0, which is going to give me 0. All right, so now that I've got that, let's see here. Yep, so we just finished 10 kilo. Next is 11. Determine the correction to range to compensate for the Earth's rotation from table hotel. Okay, so let's go ahead and extract table hotel. So the way that the step action drill for concurrent met goes is it has you extract data from tables in order. Okay, table hotel. I already see in my table hotel right here, I need to make a couple notes because I have not done this yet for charge 3. So I'm going to highlight this rockstar line. I'm gonna make sure I highlight this table because this table hotel is a tricky table. If we're not diligent, we're gonna forget to multiply our values times this down here, right? Then we're gonna make a note, note 5. When azimuth is halfway, use next highest value. Okay. All right, so let's see here. So 11 alpha. Enter table hotel with the entry range. We said our entry range was A200 over here, right? Expressed to the nearest listed value. So that's going to be 8,000, okay? And then extract the direction, and then the exact direction of fire expressed to the nearest listed value, which is the nearest 200 mils. So our direction of fire, where did we put our direction of fire, was 1400. Is 1400 a value on here? Yes, it is. It's right there, right? Okay, the value extracted is for 0 degrees latitude, must be multiplied by correction factor. Okay, so we said we were going to be 8,000, and we said 1,400, I'm pretty sure, 1,400, and then, so you're just going to come in here. Yep, so now we have this value right here, so we extract 3,2. Okay, so I extract 3,2. When entering from the top, you assign before the number, so it's negative 3,2. But we got to remember, we got to multiply by here, right? So what's our latitude? Our latitude, we said, was 20 degrees north. So 20 is going to be 94. So we have 3,2 times 0.94 gives me, wait, hold on. Whoop. So it was 8,000, 1,400. Yep, 3,2. So 3,2 multiplied times 0.94 gives me 30.08. Yep, at the bottom, let's see here. Bottom of the, yeah. Okay, so we actually record those two steps right here. Sorry, I normally perform these two steps simultaneously, but we perform those two steps here. So we got to take out the known value, which was our, the value we extracted here, which is negative 3,2. So we take negative 3,2 and we multiply that times the standard value, which for us, the standard value for table hotel is this right here. So at 20 degrees is 0.94. Okay, and so I know that a negative value multiplied times a positive value is going to yield a negative result, so I can cross through the plus column. Okay, so done. So record, let's see here, yep. So record the correction and the correction factor for change in latitude on the listed rotation met range. Yep, we just did that. Next, 11 Charlie, cross out the appropriate column, just did that. Next is multiply the correction to the range by the correction factor and change in latitude, record the result to the nearest tenth. So now we take 3,2 multiplied times 0.94, which is going to give us a negative, in the minus column, a negative 30.08, which goes to 30.1. Let me see here. Let me make sure that we express that correctly. Yep, it's the nearest tenth. Next, we go to step 1-2, determine the met range correction. 1-2 alpha. Once all multiplication is complete, total the plus column and total the minus column. let's go ahead and do that. So we're going to come over here. Let's do the plus column first. So plus column is 48.0 plus 577.7, which gives us 625.7. And let's total the minus column. Ooh. Sorry, we shouldn't be putting signs here. These should be absolute values. Okay, 58.6 plus 30.1 should give us 88.7. Okay, so we have totaled the columns. Subtract the smaller number from the larger number. Express the sum to the nearest 1 meter. So we always use bunk bed math, so the bigger number always stays on top. So that means that 88.7 is going to go on bottom. Okay, so now I'm going to take 625.7 minus 88.7, which is going to give me 537. Make sure I'm expressing this correctly. I express the sum to the nearest 1 meter. Yep, good to go. And record it out to the side of the met range correction block with the appropriate sign. So because this is in the plus column, that's going to move all the way over here. It's going to be positive 537. All right, too easy. All right, so next I got to move on to step 1.3. Determine the delta V, or the delta velocity range correction. 1.3 alpha, record the met range correction in the met range correction block and the computation of VE section. So the met range correction that we just found, which is positive 537, we just record that, whoop, right there. I'm just gonna take that, I'm just gonna pop that right there. So positive 537. Okay, so now that I have that, algebraically subtract the met range correction from the total range correction to determine the delta V range correction. So that equation is total range correction minus my met range correction gives me my delta V. Okay, so that is positive 150 minus 537 is going to give me negative 387 is my delta V range correction. Okay. Yep. Okay, so let's turn the page. We're on page 11-22 of the TC. All right, so yep, so now we determined the delta V. So in order to do that, we go to 1.4 alpha. Divide the delta V range correction by the muzzle velocity unit correction. If the delta V range correction is a minus, use the increase factor. If the delta V range correction is a plus, use the decrease factor. So we use the ditty samey diffy, right? So if this is a negative sign, that means that this also needs to be a negative sign. So which one of these has a negative sign? It's this one right here. So that'd be 19.4, right? And what do we do with that, right? We divide it. So I take 387 divided by 19.4, which gives me 19.948 whatever, which just expresses to positive 19.9. That's positive because it's a negative divided by, let's put a little division sign there, a negative divided by a negative, which gave me a positive, right? Okay, so now that I have that, let's see where we are. Delta will have the sign opposite the MV unit correction. Is it opposite? Yes, it is. Makes sense. Okay, so got that. Now we need to determine the velocity error. So we algebraically subtract the change to muzzle velocity for prop temp from the delta V. So I take delta V minus the change in prop temp, right? So for us, that is 19.9 minus positive 0.3, which gives us positive 19.6 as my VE. My velocity error, okay? Next, determine, skipped a step, so 1.6 here. Determine the pos VE. So now I take, determine the pos VE. The position VE is determined by algebraically subtracting the value of the MVV from the VE. Once the position VE is determined, circle it. Okay, so now I take this 19.6 and just pop this up here. So that's positive 19.6 minus negative 7.1. Now, do I have a delta MV weapon? No, because I'm shooting paladins right now, right? Paladins is in our known data and our situation on the first page of the homework. So that's minus 0. Okay, so that's going to be 19.6 plus 7.1 because this minus a negative value gives us positive 26.7 meters per second is our pos VE. Okay? Too simple. Okay. So now that we have that, let's move on to step 1.7. Determine corrections for azimuth to compensate for the rotation of the Earth from table India, right? And our latitude is going to be 20 degrees north. Okay, So 20 degrees, since I'm on this page, I'm gonna go ahead and highlight this right here. Highlight my rockstar line just in case I'm shooting high angle. Okay, next I select the appropriate table India on the basis of latitude, which for us we said was 20 degrees, right? Are we north or south? We are 20 degrees north, so I'm gonna enter from the top of the table, right? Let me go ahead and highlight 20 north, and this would be 20 south. Okay, looks like pretty well. Where are we? Okay, enter with the entry range. We said entry range was 8200. It's not a listed value, so I'm going to go to the nearest, which is 8000. And the exact direction of fire expressed to the nearest listed value. Okay, so direction of fire we said was 1400. So is there 1400 up top? No, but it's halfway. When halfway, use the next highest. So I'm going to go to 1600. So come together, and that would be 0.5. That would be 0.5. Okay. Next, for southern latitudes and the bottom, extract the proper correction and record it in the rotation correction block in the wind components and deflection section. So we extracted the value, right? But we have to put a sign to it. So because I entered from the top, I used the sign before the number, so it'd be left 0.5. And I'm going to input that in up here. Left 0.5. Okay, we got that. Next, I have to determine the Met deflection correction. I algebraically add the values for rotation, drift, and crosswind. Express the result to the nearest mill and record it to the right of Met deflection correction down here. Okay, so this gets a little confusing. So what we're going to do is I'm going to pretend that my lefts are all positive values and my rights are all negatives. Here I have all lefts, so I'm just going to do all positive numbers. So I'm going to do 0.5 plus 6.4 plus 0.8 plus 7.7, or correction, I'm sorry, 0.5 plus 6.4 plus 0.8, which gives me 7.7. And that's going to be left 7.7, which then expresses to left 8. Okay? So I've got that left 8. So next, go to step 1.9, determine the pause deflection correction. So take total deflection correction minus my Met deflection correction, gives me my pause. So total deflection correction is left 9 minus left 8. So think of lefts as positive numbers. So it's positive 9 minus positive 8, which is going to give me positive 1, which means, so positive is going to be left, so this could be left 1. Pause deflection correction is left 1. All right, making progress. Okay, so we've got that. Next, I determined from table Juliet the unit corrections for fuse. So 20 alpha. Enter Juliet with the fuse setting corresponding to the adjusted elevation expressed to the nearest whole fuse setting increment, which is what we found down here of 2.1, right? So extract our TFT. Let's go to Juliet. Okay, so we said it was 2.1, right? Whoop, there we go, 2.1. Okay, so got it. Extract the correction for delta V from column 2 for a decrease or from column 3 for an increase of delta V, right? So I should have recorded my delta V down here. So delta V is an increase of 19.9. I got that from right here, right? Okay, so delta V, we said we have an increase. So increase column at 2.1 seconds, I get 0.031. So that's my correction. Positive 0.031. And then I can follow the rest of the steps, but it's just going to tell me to keep going down here, right? So range wind. So do I have a head or a tail? I have a headwind, so 2.1 seconds with a headwind would be negative 0.001. Next is air temperature. Air temperature, I have a decrease, 0.013, positive 0.013. Next, I have air density. I have an increase in air density. So that's negative 0.030. Next, projectile square weight, which it's going to be 0 because I am using standard, which is 4 square. Okay, so after I have that, a plus column and a minus column, basically figure out my columns. So a positive and a positive is going to be a positive, so I can cross out this minus column. A positive and a negative is going to be a negative, so I can cross out the plus column. Okay. Air temp, so a decrease, so a negative or correction, I'm sorry, a positive and a positive is going to be a positive, so I can cross out the negative. Air density, positive and negative is going to be positive, so I can cross out the minus column. And then projectile square weight is not going to be either. Okay, so it looks like I've just got one. Oh no, I'm sorry. So positive and negative, that will yield a negative result, so that should be, correct that. So right, positive 0.2 multiplied times negative 0.030 would yield a minus. So I'm going to cross out this plus here. Okay, my bad. All right, so now that I have that, I can go ahead and multiply across. 19.9 times 0.031 is going to give me 0.6. Make sure I'm doing that right. 19.9 multiplied times 0.031 gives me, yep, 0.617. Okay. Next is 8 times 0.001, which is going to give me 0.008. All right. Then I have 0.2 multiplied times 0.013, which is going to give me 0.263. Fix that 0 there. Okay. Next I have 20.0 multiplied times 0.030, which is going to give me 0.606. Okay. After this, let's go back to the step action drill, but it's going to tell me to add all the columns. Let's see here. Okay, determine the met fuse correction. We multiply the variations, which we just did. Total the plus and total the minus, right? Subtract the smaller number from the larger number, express sum to the nearest 0.1. So let's add all the columns. So 0.617 plus 0.263 gives us 0.880. And 0.008 plus 0.606 gives us 0.614. Okay, now we have that. Let's do bunk bed math. Smaller number goes on the bottom. So that's 0.880 minus 0.614. It's going to give us 0.266. Okay. 0.266, I now take that, and that is now my met fuse correction. So I'm going to put that up there and express that to the nearest tenth. So that is in the plus column, so that is a positive 0.3. All right, and record the met fuse. Yep, so done, and then almost done here. Next, step 2.2, determine the pos fuse correction. Algebraically subtract the met fuse correction from the total fuse correction. The result is the pos fuse correction. So it's total fuse correction minus the met fuse correction. So negative 0.2 minus positive 0.3, so that turns it basically into a minus. So that's minus 0.5. Negative 0.5 is my pos fuse correction. Okay. So now that is how we execute a concurrent met technique. So the things that I need out of this, right? I enter this with a GFT setting, known data, and a met message, and I leave with my isolated pos constants, my position deflection correction, right? Which is, there is something affecting how far I have to aim my howitzer left or right, right? I don't know what it is, but I can account for it now because I've stripped away all of my big blue met. So now I know my pos deflection correction is left 1, so I can transfer that to my adjacent unit. My pos velocity error, or basically my range correction, that I have to account for. I don't know what it is. Something is affecting like my range correction. I don't know what it is, but I can quantify it, right? So it's positive 26.7 meters per second is my pos VE. I can transfer that to another unit. And then down here, my fuse correction, my pos fuse correction is negative 0.5. Something is affecting the way or the height of burst of my fuses. I don't know what it is. I can't identify it, but I can quantify it. And I can quantify that as subtracting 1/2 of a second from every time fuse that I shoot. And then I can transfer that over to my adjacent unit. So that's my concurrent met technique. So let's go ahead and finish up the homework with requirement 3. Okay. So requirement number 3, you receive a movement order from the battalion FDO to move to a new firing point. He informs you that the battalion survey team is awaiting at your new point. He tells you that Charlie Battery conducted registration earlier using charge 1. What is the charge, which is the charge you will be firing at the new firing point? Okay. What procedure must you conduct in order to fire accurately under these new conditions? So we have not taught you how to do this yet. This is in the next class, but it's going to be a subsequent MET technique. Which is basically like, hey, Charlie Battery just shot a registration, which means they isolated their pause constants. So when we occupy a new position, and if we're shooting with their same charge that they're shooting with, they can give us their pause constants. We can apply that to a DA Form 4200 and get our new total corrections without having to shoot a registration. And that's called a subsequent MET technique. I know that's not how you spell technique, but a subsequent MET technique, okay? So number 2, what is the result of this procedure? Correct. Choose the correct answer. So subsequent MET technique is basically like, hey, I've got a MET message. I'm tracking all my fire requirements. I've got my new pause data. What is that going to give me? Even without shooting a registration, it's going to give me new total corrections. Okay. There you have it. That is the completion of the registration theory homework, specifically using the concurrent MET technique.